Welcome to Chem 313, lecture number 3, where we're going to pick up where we left off last time. So to review, we previously discussed all the different intermolecular forces that are important in biology. That was mostly in lecture 1, although we gave a brief review over in lecture 2 a bit. But then we discussed the basis of acids, bases, and buffers in lecture 2. And I think the key lesson from buffers is we defined a buffer as a mixture of a weak conjugate acid and conjugate base. And these solutions resist pH change whenever acid or base is added. And this is important in both living systems and also in experiments, because as we're going to start to appreciate beginning with today's lecture, biological matter has different available intermolecular forces at different pHs. It's supposed to say available. I don't know what the hell I was thinking when I wrote that. Anyway, we saw before that there's this concept of a pKa. So a pKa is defined as the pH at which the concentration of a weak acid is going to be equal to the concentration of its conjugate base in solution. However, you can think of, because pH is a variable, you can think of a pKa as the point in pH space at which a molecule changes in electrical charge. And that's going to be very important going forward when we talk about amino acids, which is the subject of today's lecture. So let's review a little bit acid and base chemistry. So we will define an acid in the Bronsted-Lowry definition as a proton donor and a base as a proton acceptor. And we're going to define a buffer as we already did on the last slide, which is a mixture of a conjugate acid conjugate base pair. So let's take a look at such a pair. What we have here is a phosphate ion. Strictly speaking, this would be a monobasic phosphate ion. And in the presence of water, it can give up one of its protons, or H+ ions, to give us a so-called dibasic phosphate ion and hydronium, H3O+. So in this case, H2PO4- is our conjugate acid. Water in this case is acting as a base, because remember, in the Bronsted-Lowry system, you can never have an acid without a base. There's always one accepting the proton and one donating the proton. HPO4 is the conjugate base partner of HPO4-, and H3O+ is the conjugate acid of the water. So the two are related in that way. Now, Phosphate, which is what we have here, is useful as a buffer. So in a phosphate buffer solution, we have appreciable amounts of both H2PO4 minus and HPO4 2 minus at the same time in solution. So because this chemical reaction right here is an equilibrium, then at equilibrium, the concentration of nothing is going to be changing, and so we will have a certain fixed amount of the two different forms of our phosphate. Now, let's imagine the situation where we take a strong acid, we'll say HCl, and add it to water. So because HCl is a strong acid, when we mix it to water, we don't have an equilibrium. The reaction just goes to completion, and we're left with H3O plus and Cl minus. So that means that however many moles of HCl we start with, we're going to end up with X moles of H3O plus when we're done. Now, let's instead consider the case where we add HCl to a phosphate buffer solution. What's going to happen in that case is that our HCl is going to protonate not so much the water, although that will happen to a small extent, but our conjugate base. Right? And this time, again, because it's a strong acid, if we add X moles of HCl, that means we have gained X moles of conjugate acid and lost X moles of our conjugate base. But what we have not really done here is changed our hydronium concentration. And that's the principle of buffering action. Now, however, it does not mean that the hydronium concentration and the pH doesn't change at all. It does change some. And why is that? Well, look at what we just did here. We increased the concentration of H2PO4 and we decreased the concentration of HPO4 2 minus. So if we go back to our original equilibrium, what happened over here is the concentration of this compound went down, the concentration of this compound went up. And so thinking back to Le Chatelier's principle, if you increase the concentration of a reactant and decrease the concentration of a product, what's going to happen to the equilibrium? The equilibrium gets pushed to the right. And as a result, our H3O concentration will go up slightly to reset the equilibrium, and therefore the pH will go down, which is what you would expect because you're adding an acid. If we'd added a base, the opposite would have occurred. So we said last time that whenever you have a buffer system, you can make a graph of pH as a function of the ratio of conjugate base to conjugate acid. In this case, that would be HPO4 2 minus on top over H2PO4 on the bottom. And we said that this graph has a shape that looks something like this. In the middle, The flattest part of this graph is the point where this ratio is equal to 1, and that's the point at which the concentration of conjugate acid equals the concentration of conjugate base. And at that point, the pH of our solution is going to be equal to the pKa. So remember, the pKa of a given acid-base pair is a constant under a given set of situations. So the pKa for the phosphate ion that I've given here is around 6.9, right? You don't have to worry about knowing that value. But what is this telling us? So this is telling us that whatever pH we start at, we can keep adding a little bit of acid or base up to a certain point, right? So let's say that we had the situation we did before where we are going to add HCl, a strong acid, to give us more of our conjugate acid, so that our concentration of conjugate base decreases and our concentration of conjugate acid goes up. Well, what's that doing to our ratio? That's causing the ratio to decrease. And eventually we're going to reach a point where our ratio of base to acid is going to be equal to 0.1. And at that point, usually the pH curve starts to roll off quite dramatically. At this point, the pH is going to be equal to the pKa minus 1. If we'd added base, we could have done the same thing on the other side. Adding base increases the ratio. And at that point, our pH is going to be equal to the pKa plus 1. So this zone here in the middle, where our curve is relatively flat, is what's called the buffering range. And that's the zone of pH in which your buffer is fairly resistant to change in pH. And then we have something called the buffer capacity, and the buffer capacity is related to how far you can go on the x-axis. If you're starting off at this pH value right here, then this horizontal arrow represents the capacity for added acid. So our buffering capacity is the number of moles of acid that can be absorbed without going outside of the buffering range. And it's proportional to the concentration of buffer. Our capacity for added base would be that much over there. So at this point, the question becomes, why does it matter so much that buffers resist changes in pH? Well, the answer to that has to do with the fact that anything with titratable groups, so that means anything that can gain or lose a proton, has a variable charge at different pH values. This is why we really care. So for example, let's take a look at phenol. So phenol is a weak acid. Water is a weak base. And if you have phenol in water, you're going to have an equilibrium in which we have lost our proton and we have an H3O+. This would be our conjugate base. So this is an equilibrium. It has a certain equilibrium constant associated with it, and therefore it has a P of the equilibrium constant. Remember, P is simply minus log of Ka. And as it happens, the pKa for phenol is right about 10. So what is that saying to us? Well, what that's saying to us is that if we are at a pH that is below the pKa, whenever your pH is lower than the pKa, that means that you're going to have more of your conjugate acid than conjugate base. Now, there's an important way that you can rationalize this. Just think of Le Chatelier's principle, right? If you add H3O+, pH should go down, right? Well, if you add H3O+, what's happening over here? If you are at pH below your pKa, that means you have more H3O+ than you would at a higher pH. The more H3O+ that you have, the more this equilibrium gets pushed to the left, and we end up with more of our conjugate acid. Likewise, if your pH is above your pKa, that means that the concentration of conjugate base will be greater than the concentration of conjugate acid. And you can rationalize this by Le Chatelier's principle in the same way. If your pH is high, that means you would have a low concentration of H3O+. If you have a low concentration of H3O+, the equilibrium pushes to the right, and we end up with a higher concentration of our conjugate base. So in other words, and I said this last time, pKa is sort of a tipping point. Whenever pH rises above a pKa, your molecule is going to either gain a negative charge or lose a positive charge. And vice versa, whenever pH drops below a pKa, your molecule will either gain a positive charge or lose a negative charge. For example problems here, I'm going to recommend that you take a look at worksheet 2, which should be up on Canvas, and it has a couple of good practice problems on it. This is a concept that I think is absolutely critical for you to understand, the relationship between pH and electrical charge. Whenever pH is lower, biomolecules are going to be more positive. And whenever pH is higher, your biomolecules will be more negative whenever you have water as a solvent. This is a general case, and we're going to see it come up time and time again in this course. Okay, let's move on to some new material now that we've done some review. We're going to talk about building blocks. So in lecture 1, we talked about that hierarchy of living matter, and I said that you can have inorganic molecules. We called them inorganic precursors, which can then react together to give us small organic molecules that we called metabolites. And the metabolites can then be put together into somewhat larger but still fairly small organic molecules called building blocks or monomers, which then assemble into polymers or macromolecules. So we're going to take a look at building blocks. So we're going to define building blocks as relatively small organic molecules containing, I'm going to say, two things. The first thing is complementary functional groups. And the second factor is some sort of structural diversity. All right, what do I mean by both of those? I'm going to give you guys an analogy. The analogy is Legos. So Legos are a building block, a literal building block. So how do Legos work? Legos work by having two structural features. You've got the bumps or knobs or whatever they're supposed to be called, and you've got the little sockets on the bottom that the bumps plug into. So if you take two Lego pieces and you plug one together with the other, what do you get? Well, you stack them up like this so that the bumps on one plug into the sockets on the other, and we're left with a larger piece. So the bumps and the sockets are analogous to our complementary functional groups. They react to give some sort of a stable chemical linkage. In the case of Legos, it's obviously not a chemical linkage, it's friction, but you get the idea. There's a stable linkage being formed by these different groups reacting together. But notice something else here. Once we've put our two building blocks together to give us our new Lego piece, we still have complementary functional groups left over. Which means that we can add another Lego brick if we wanted to and keep going, so that now we have three stuck together. And from those three, we still have our bumps and our sockets in place that are still free to undergo different reactions. So that's what's meant by complementary functional groups. It's something like the bumps and the sockets on Lego pieces. When you react them together, you get a stable linkage, and you end up with a larger piece that still has the same complementary functional groups, the same bumps and sockets, so that you can keep going. All right, so that takes care of the complementary functional groups, but what do we mean by structural diversity? What we mean by that is that our Lego bricks aren't just the little 2x2 square pieces. You've also got the 4x2 square pieces. Or you have the, long, super flat ones. And you even have the little single pieces. This is our structural diversity. We have different shapes. Or in this case, different chemical properties. If you're talking about biological building blocks, but they're all capable of linking according to the same chemistry. So an example of a molecule that could be a building block, in reality this is not a biological building block, would be something kind of like this. Some molecule that has an alcohol group and a carboxylic acid group. So if you were to take two of these and react them together, what you would end up with would be something like this. Recall that alcohols and acids can react to form esters. And what we've done by reacting two of these molecules together is that we've formed an ester linkage that joins them, but we still have our complementary functional groups. And then water is formed as a byproduct. So we have a condensation reaction taking place here. We could introduce some structural diversity by having different versions of this molecule. So for example, we could have, say, one with a methyl branch on there, and we could have, I don't know, one with a double bond, say. And so by mixing and matching our molecules, we would end up with similar linkages once again. Now we have two esters, but we still have our complementary functional groups, our OH and our COOH, and we would lose two waters as a byproduct. So this is what building blocks look like in biological space. All right, so the building blocks that I just showed you, the esters, that's not something you see a whole lot of in biology. What we're going to talk about today are the amino acids. These are probably the single most important building blocks in all of biology. So in amino acids, they are the building blocks of a class of molecules called polypeptides. And polypeptides consist of peptides and proteins. And the difference between those two is just the size. Proteins are the bigger ones. So for amino acids, our complementary functional groups are an amine and a carboxylic acid. So this is what all amino acids look like. We have a so-called alpha amine. We have a carboxylic acid group. We have a hydrogen, and we have this variable group that's called R. So according to the rules of organic chemistry, this carboxylic acid group is defined as carbon number 1. This carbon in the middle is called the alpha carbon, and therefore this amine group over here is called the alpha amine. And notice the way that I've drawn this structure. We have a negative charge on the carboxylic acid and a positive charge on the amine. This is what the structure of amino acids looks like at near neutral pH. A lot of times you'll see amino acids written like this. And while that's not completely incorrect, it's also not very realistic, especially if you're in water. And the reason for that is because the amine group is pretty basic. and the carboxylic acid group is acidic. And so if you put this thing into water, what's going to happen? What's going to happen is this hydrogen is going to go right over there, and we're left with a zwitterionic structure. Now, the way that amino acids react together, just to jump ahead a little bit, is like this. Whenever you have an amine and a carboxylic acid together, they can react to give you an amide. So what would that look like? It's going to look like this. Now we have R1. Our carboxylic acid loses an OH. And we are left with an amide linkage. And in biochemistry, we call this a peptide linkage for reasons that have never been fully clear to me. And then water is released as a byproduct. So the complementary functional groups are our amine and our carboxylic acid. These variable groups, the R's, these are what are known as side chains. And these are what give us our structural diversity. All right, so this slide summarizes and shows you a nice little clean picture of all the different amino acid details that I've already been talking about. Amino acids are the building blocks of peptides and proteins. We have an amino group and our carboxyl group. When those two get added together, you get an amide. And again, in biochemistry land, we always use the term peptide linkage rather than amide, but they're the same thing. Now, something you should notice about all of our amino acids, with one exception, is that if you were to look at these molecules, your alpha carbon is at the center of a tetrahedron, and it's got 4 separate groups connected to it, therefore, it's chiral. So it's chiral around that alpha carbon in the middle. So possibly you would have to deal with multiple enantiomers, but lucky for us, all of our amino acids have the L configuration. The L configuration is relative to glyceraldehyde, if you're familiar with that. If you care about the absolute configuration, it's not quite so simple, but luckily I don't expect you to know that. So all of our amino acids are tetrahedral. Our side chain is variable. And the side chain determines the identity of the amino acid. All right, so our side chain or our R group determines the identity of the amino acid. There are 20 different amino acids that are found in proteins. That does not include a couple of extremely rare amino acids that are only seen in weird niche bacteria. And it does not include chemically modified amino acids, which is something that does happen in living cells. There are simply 20 standard amino acids found in proteins that you need to be familiar with. So all of these have the L configuration, except for glycine, which is the one that is not chiral. In glycine, the R is simply a hydrogen. Therefore, it's not chiral. And then absolute configuration, if you care about that, I'm just going to mention it in passing, that it's S for all of them except for cysteine, which is R, and I'll leave it as an exercise to you to figure out why that is. All right, so these are our 20 standard amino acids. You are not responsible for memorizing these. However, you are responsible for knowing their properties and which groups belong to which. So notice that our amino acids separate into several different groups. okay? You should at least know the groups of amino acids and their general properties. If you want to memorize the structures of all the amino acids, that would be perfectly fine. I think that would be the safest bet, but I'm not going to specifically quiz you guys on any of these structures, so don't worry about that. So different textbooks divide up the amino acids different ways, but they usually have certain things in common. So we've got roughly half of our amino acids have nonpolar side chains. When we say nonpolar side chains, we mean that the R group is mostly, not entirely in most cases, carbon and hydrogen. Right, so glycine could be considered a nonpolar amino acid. The side chain is just hydrogen. Alanine, it's a methyl. Valine, it's an isopropyl. Leucine, we get an isobutyl, right? And it just keeps going from there. Isoleucine, it's sec-butyl and blah, 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 right? And then some of them get a little bit fancier. So tryptophan has this complicated ring that's called an indole. Methionine actually contains sulfur, which doesn't affect the polarity that much. We then have some amino acids with polar side chains. I want to qualify that. These are polar but non-charged. So we don't have an electrical charge on them. So serine and threonine have alcohol groups in there. Cysteine has an SH that's not exactly a polar side chain, but I understand why they put it in there. And then asparagine and glutamine have amides on the side chain. And then we have the charged amino acids at the bottom. So we've got two that are, this figure says acidic, but I prefer to think of them as negative at pH 7. And then we've got basic, which are positive at pH 7. All right. Every single amino acid table that I've ever seen in my life infuriates me in some way. And so the one I choose to show in my slides is the one that infuriates me the least. And the problem I have with this table, what infuriates me about this table, is this one right here. Histidine is put in the positive at pH 7 column. That's not strictly speaking true. Histidine has a pKa of about 6. So it's actually neutral at pH 7. It belongs up here, right? The reason they put it there is because there's always a small fraction of histidine that will have a positive charge at pH 7 because, once again, pKa's, it's not a switch. You go from all positive to all neutral or vice versa. It's a population. So at pH 7, about 1 in 10 histidines could be expected to have a positive charge. Now, notice something about all of our amino acids. With one exception, everything that is not an R group is all the same. It's only the R groups that are highlighted in color that are different. And so really, it's the side chains that dictate the property of your amino acid. So to summarize this slide, I would say know the different groups of amino acid. Know which ones are nonpolar, know which ones are polar, know which ones are going to be negative at neutral pH and which ones are going to be positive at neutral pH, keeping in mind that histidine is actually neutral at pH 7. And then figure out on your own which intermolecular forces each of these amino acids is capable of experiencing. Okay, so you can divide up your amino acids into your own groups if you want, right? So I recommend that you think of amino acids with a negative charge at neutral pH as glutamic acid, also known as glutamate, aspartic acid, which is aspartate. Glutamate is this. I'm going to use a condensed structural formula here to save time. And aspartate is almost the same thing, but with one fewer CH2 on the side chain. Okay, now, what do we notice about these amino acids here? Once again, the alpha carbon, the alpha amine, and the carboxylic acid group are identical. The only difference is in the R chain. And notice that for both of these amino acids, we have 3 titratable groups. Now, the structures that I've shown here are what would be predominant at pH 7. We have 2 carboxylic acids. The one that's on the alpha carbon has a pKa of right around 2.5 to 3. The side chain has a pKa of about 4. Our alpha amino group has a pKa of around 9 to 10. So if you can remember these structures, I think you'll be in good shape to figure out what the charge on these will be at different pHs. Now, in practice, we don't usually worry about the pKa's of the alpha carboxylic acid or the alpha amine, for reasons that'll become clear in a moment. We only care about the pKa's of the side chains. So notice that because at pH 7 our amine is positive and our alpha carboxylate is negative, we have a zwitterion. And so it's the charge of the side chain that determines the charge of the amino acid. So this is true of nearly all amino acids. Whenever you're near neutral pH, and by that I mean pH from about 4 to about 8 or so, actually higher than that, 4 to about 10, the charge of the side chain is going to equal the charge of the amino acid. And you should be able to figure out what would be the charge on any one of these at a given pH value, as long as you're given the structure of the amino acid at a different pH value and all of its pKa values. So we already said that the side chain pKa for glutamates and aspartates is around 4. And what that means is that if your pH is below that pKa, we'll say our pH is about 3, the structure of our amino acid becomes this. And at a pH of 3, now what's the charge on our molecule? Well, the charge at pH 7 is going to be 1 minus. The charge at pH 3 is 0. And what do we notice? We notice that as we drop from pH 7 to pH 3, our charge goes from 1 minus to 0. So once again, as pH drops, your charge becomes more positive. All right, positive charge at neutral pH. There's 2 of those too, lysine and arginine. These guys are not as easy to draw. That's lysine. Arginine has a crazy side chain. That's arginine. But once again, The main group is going to be the same. It's the charge on the side chain that dictates the charge of the amino acid. Arginine has a pKa value of right around 12, which means that it's going to be positively charged until you get up to a pH of 12 or above. So in effect, always it's going to be positively charged. Lysine has a pKa of around 10.5. And then we have two amino acids that can become charged not necessarily at neutral pH, but charged near neutral pH. And those are cysteine, which has a pKa of about 8, and it's neutral at pH 7. And we have histidine, which has a pKa of about 6 and is neutral at pH 7. So what that means is that if you raise the pH up to, say, 8.5, cysteine, whose R group is SH, is going to lose a proton and become S-. So this is the form that predominates at pH above 8. Now, why do we worry about these guys becoming charged near neutral pH? What that means is that if you are right at neutral pH, a small fraction of these will be charged. And the reason for that is because of the Henderson-Hasselbalch equation. Remember, these are ionizable groups, so the Henderson-Hasselbalch equation applies to them. Let's take a look at cysteine. So for cysteine, this would be our conjugate acid form, and the S- would be the conjugate base form. So if we're at a pH of 7 and the pKa of cysteine is 8, what is that telling us? Well, what that's telling us is that the log of A- over HA must be equal to -1. And what that means is that our concentration of conjugate acid is 10 times the concentration of conjugate base. So 1 in 10 cysteines will be in the S- form. Another thing to notice about amino acids, which is not related to the charge specifically, but I forgot to comment on it on the past slide, is that amino acids tend to be abbreviated when they're written with 3-letter codes and also 1-letter codes. So you are not required to know the abbreviations. In any problem that I give you, these will be provided. So for example, lysine, its 3-letter code is LYS. Notice that the first letter is always capitalized. And the 1-letter code is capital K. That may not make any sense, but capital L is a different amino acid. That's leucine. Do not confuse leucine with lysine. Leucine is abbreviated LEU, and it's capital L. Arginine, that would be ARG, and its 1-letter code is R, which is kind of phonetic. So all of that you can get from the table, which once again is going to be provided to you. You don't need to memorize. All right, so we already saw in the last slide that there's some amino acids that can function as acids or bases, right? So the amino acids that can function as acids would be glutamic acid or glutamate, aspartic acid or aspartate. In rare cases, cysteine. Some can function as bases. We already saw those, arginine, lysine, and less frequently, histidine. And notice that because these two become protonated near neutral pH, they have pKa's near neutral pH, these can function as both acid or base at near neutral pH. But there are some other useful and important properties of certain amino acids as well. We've also got the aromatics. The aromatics are phenylalanine, tyrosine, and tryptophan. So for those, what does our R group look like? For phenylalanine, it's a phenyl ring on a CH2, so it's benzyl. For tyrosine, it's basically the same, except we've got an OH in position 4 on that ring. And for tryptophan, it's a bit different. We've got an NH in our side chain, and we've got 2 fused rings. So why do we care about the aromatics? The aromatics absorb UV light. So you'll recall that whenever anything absorbs light, there is a certain wavelength we call the lambda max, which is the wavelength of maximal absorption. That's the wavelength that it absorbs the most. And for most of these, that's right around 280 nanometers. So you'll recall from Beer's law, you can write the absorbance of a compound in solution is proportional to its concentration times the path length, the distance the light has to pass through the sample, times this epsilon, which we call the absorptivity. And as it turns out, the absorptivity at 280 for phenylalanine is fairly low. It's much higher for tyrosine, and it's very high for tryptophan. So this is actually handy because if your protein or peptide has tyrosine or tryptophan in it, you can use absorption of UV light to measure the concentration of these compounds. Another important amino acid that I'm going to introduce right now, but we're not going to talk about why it's unique until a bit later, is proline. Proline has an odd structure. Proline is the one amino acid where the R group is connected to the nitrogen. All right, by touches, I should say bonded to. And so because of this, we actually have a ring that's a part of this main part of the amino acid here. And because of that, it's conformationally restricted. And that's going to come out to be important later on, as we will see. And then the last sort of interesting amino acid that I think is worth talking about, once again, is cysteine. So cysteine is the one, once again, where the R group is CH2SH. So not only is cysteine capable of acting as both an acid or a base, but this SH is highly reactive. And cysteine does something that no other amino acid does. If you were to take 2 cysteines they can undergo a reaction like this. There's one cysteine, there's the other. They react together and give us an SS linkage where the two cysteines are connected together. And then for this to happen, 2 protons are lost and 2 electrons are lost. This is what's called a disulfide bridge or a disulfide bond. So that's the unique thing that cysteine does. In many proteins, cysteine actually forms this disulfide group together like so. Some textbooks, if a cysteine is in a disulfide, it's written as cysteine. Notice the spelling is slightly different. Not all textbooks use that terminology. And what we have here is a covalent bond. And this is actually very important in protein structure for reasons we're going to talk about pretty soon. All right, so what is a polypeptide? Polypeptides are polymers of amino acids formed by condensation reactions of the alpha amine group and the alpha carboxylic acid group, are 2 complementary functional groups. So this is the situation that we saw before. Our 2 amino acids react to form a single molecule. And water. And we are left with a linkage between these that is an amide group. The term that we always use in protein chemistry is a peptide bond. That's something of a misnomer. The word peptide doesn't really have a well-defined meaning, and it's not one bond. There's multiple bonds there. But we call it a peptide bond or a peptide linkage. So what a polypeptide really is a chain of amino acids joined by peptide groups. And the peptide linkage would be this, CONH. So there's 2 different types of polypeptides. Polypeptide is a generic term. The term peptide refers to a short chain. And what is short is relative, but usually it's going to be less than 50 amino acids or so. A protein is the same thing, but longer. Generally more than about 50 amino acids, although it depends on context somewhat. So what all polypeptides have in common is peptide bonds. What we have is a chain of peptide bonds and a chain of R groups on the side. All right, so this is sort of the anatomy of what a peptide molecule looks like. So what we have here is what would be called a pentapeptide. Which means we've got 5 amino acids linked together, and we have a big long chain like so. So what do you notice about this molecule? What we notice is that we can look at it as almost like a comb or a brush type structure. We have this repeating sequence of atoms, nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon, and so forth that keeps going. So the nitrogen to carbon part is going to be our peptide bonds. So you can think of a peptide as a repeating sequence of peptide bonds with one carbon group in between them. Those one carbon groups in between them are our alpha carbons. Now, notice that we have this sequence of peptide bonds, but at the end of the chain, you don't have peptide bonds. You still have your free complementary functional groups that are available to react with more amines. So what happens is we are left with a free amino group at one end of the molecule and a free carboxylic acid group at the other end of the molecule. And these ends of the molecules have special names. So the one end of the molecule that has an amine on it is called the N-terminus, or the amino terminus, and for nitrogen. And the other end has a carboxylic acid group, so it's called the C-terminus, or carboxy terminus. And notice here that at neutral pH, the N-terminus is going to be positively charged, and the C-terminus will be negatively charged. So the two cancel each other out, but the charges on the side chains will decide the charge of the peptide molecule. All right, and notice that at every one of these alpha carbons, we have an R group hanging off of the side. So this repeating chain of nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon, this part of the molecule is referred to as the main chain, also known as the backbone. And then our R groups hang off the side of the backbone. They're not part of the main chain. They come off the side, so they must be the side chains. That's where the term side chain comes from. So there is a term that we use to define polypeptides, and that's what's called primary structure. So the primary structure is simply the amino acid sequence of a polypeptide. It's the sequence of amino acids in a polypeptide read by convention from the N-terminus to the C-terminus. So by convention, we start numbering our amino acids at the free amine and finish at the carboxylic acid group. That's why I numbered these amino acids up here, R1, R2, R3, R4, and this would be R5. So as we're going to see in the next lecture, the amino acid sequence determines both the identity and the chemical properties of a polypeptide molecule. You can have two separate polypeptides that have the same amino acids, just in a different sequence, and they're going to have very different physical properties and very different chemical properties for reasons that we're going to talk about over the next few lectures. So for now, understand that a peptide is a sequence of amino acids linked together by peptide linkages. We have a repeating chain of nitrogen, carbon, carbon, which is our main chain. We've got our amino acid R groups, which are our side chains branching off the side, and that the primary structure is just the order that they all come in. How primary structure determines the properties of these molecules we'll talk about in the next lecture.